Good morning. Now we will start the second session of our module 1. The first session was wave motion that we have completed, and now we are going to start the second session of our module 1, which is oscillations. Okay, so this is the first class on oscillations. Now here you have to study a few definitions. That is sometime I think you might have heard about these terms in your lower classes, I mean 12th standard. So see, what is meant by periodic motion? As the name suggests, something or as a motion that repeats itself at regular intervals of time is called a periodic motion. That is, if a motion is repeating at a regular interval of 10 seconds, then you call it as a periodic motion. Okay, so any motion which repeats itself at regular intervals of time is called periodic motion, and some examples are orbital motion of earth around sun, motion of clock pendulum, vibration of atom in a molecule, vibration of prongs of a tuning fork, etc. Okay, so here you get a definition. What is periodic motion? Give examples. Okay, first question. Then what is meant by period? Then the time period or the time required to complete one round trip of motion is called a period. Another definition. Then so you have studied the definition of periodic motion now, right? Now if that particular periodic motion, if it is confined or if it is restricted to well defined boundaries or limits called extreme positions, then you call that periodic motion as an oscillatory or vibratory motion. That is, if the periodic motion is confined to well defined limits called extreme positions, you call it as a oscillatory or periodic vibratory motion. So there is another definition. So in an oscillatory or vibratory motion, it is nothing but a to and fro motion. That is a system moving forward and a system moving backward. So to and fro motion. That is called an oscillatory or vibratory motion. So when you are asked to define what is oscillatory or vibratory motion, you can write, if a periodic motion is confined to well-defined limits called extreme positions, then it is called oscillatory or vibratory motion. Here it is a to and fro motion. Some examples are oscillations of a freely suspended bar magnet, oscillation of a loaded spring, etc. Okay, so here you got three definitions. Which are they? Define periodic motion, give examples. Then what is period? Then define oscillatory or vibratory motion, give examples. So from this you have got three definitions. Now please note that all periodic motions are, all oscillatory motions are periodic. Okay, but all periodic motions are not oscillatory. So just keep in mind that point. Okay, why? Because the orbital motion of earth around the sun, okay, that was an example for periodic motion, but it is not an oscillatory motion. Why? Because it is not a to and fro motion. Earth is orbiting around the sun. Okay, that is, it is revolving around the sun. That is not a to and fro motion. That is why we say that all oscillatory motions are periodic, but all periodic motions are not oscillatory. An example is orbital motion of earth around the sun. Here earth is revolving around the sun, so it is a periodic motion, but since it is not a to and fro motion, we cannot categorize it under an oscillatory motion. Okay, now this periodic motion arises mainly due to some properties like elasticity, inertia, etc. That is, suppose that you have a oscillator uh, uh, at an equilibrium position. Equilibrium position means stable position. Okay, suppose that you have an oscillator at equilibrium position, and now you are applying a force and you are displacing it from that equilibrium position to another position. Okay, that is, you are applying a force so as to displace an oscillator from its equilibrium position. So when doing so, a restoring force, that is somewhat like a frictional force, will act And why does that act? In order to oppose that displacement. Okay, that is a restoring force will develop in order to oppose that displacement. That is, that restoring force will try to bring that oscillator back to its equilibrium position. Now, this restoring force, thus acting, mainly depends on the elasticity of the system. Okay, so you are trying to displace an oscillator from its equilibrium position by applying a force. When you do so, a restoring force acts on the same time so as to bring the oscillator back to its equilibrium position. At the same time, uh, inertia will come into play. It will oppose that effect. So actually elasticity and inertia plays an important role while you are trying to displace an object from its equilibrium position. So because of the effect of inertia, even though that oscillator come back to its equilibrium position, it will overshoot the original position. Okay, that is mainly because of the effect of inertia. So from this we can understand that the periodic motion of any object is always under the effect of two factors, which are the elasticity and inertia. Now, so this you just read this paragraph. From here you got three definitions. What is periodic motion? Give examples. What is period? Then what is oscillatory motion or vibratory motion? Give examples. Okay. This is just for your information. Just understand the concept. That is enough. Now the other important topic is this one. That is, what is simple harmonic motion? I think this you have studied in your 12th standard. What is it? Simple harmonic motion. It is an oscillatory motion in which particle moves to and fro about mean position, that is equilibrium position. How? In such a way that these 2 points are very important. That is, in such a way that restoring force acting on the particle at any instant is directly proportional to displacement, and this restoring force is always directed towards the mean position. So when you are asked to define simple harmonic motion, you have to specify up to this one. Okay, now any particle executing simple harmonic motion is called a simple harmonic oscillator. Now some example is oscillating pendulum is an example for simple harmonic motion. Then other one is, suppose that you have a mass attached to a vertical string, like that a mass is attached to a vertical string. Now this one end is fixed, then vibrations executed by this mass is actually a simple harmonic motion. Okay, so these are few examples. Then this simple harmonic motion can be either linear or angular. Okay, we call it as a linear simple harmonic motion if the particle move along a straight line under a constant force. Now we call it as an angular simple harmonic motion if the particle is rotating about an axis under a constant torque. So see the difference. When it is a linear motion, it is a straight line under the action of constant force. Okay, if it is an angular one, it is rotation under constant torque. Okay, now here we usually use, in order to express the simple harmonic motion, we use sine and cosine terms or functions. Why? Because the sine and cosine functions are periodic, at the same time they are bounded. That means they exhibit oscillatory conditions and they have a period of 2 pi. So in most simple harmonic expressions we use either sine term or cosine term. So here, which is the question? What is simple harmonic motion? Give examples. Okay, so this is a definition, then you give example. Then another question is distinguish between linear and angular simple harmonic motion. Okay, that's all to study from that slide. Now another possible question, that is derive differential equation for a simple harmonic motion. This is very simple. That is, consider a particle of mass m. It is attached to a spring of force constant k. Suppose that the mass is negligible, then you draw that figure. Now suppose that the mass is displaced from its equilibrium position, then as I already said, it will experience a restoring force. What does the restoring force do? It will try to bring the particle back to its equilibrium position, right? Now at any instant of time, say t, let x be that displacement. Then what will be the acceleration? If x is the displacement, then you know velocity is dx by dt. Then what is acceleration? It will be d square x by dt square c. Okay. Now for a simple harmonic motion, as I already said, this restoring force, as per the definition, we have learned that restoring force is always proportional to displacement and is directed towards the mean position. So you can write restoring force, that is forces mass into acceleration, right? That is m into d square x by dt square. That is your restoring force. It is directly proportional to displacement x. But since it is directed opposite to the direction of displacement, we put a negative sign. That is why we write dm d square x by dt square proportional to minus x. Now in order to remove that proportionality sign, you remove that proportionality sign, put an equal to, and you are introducing a constant of proportionality k, which is nothing but spring constant. Now on rearranging this equation, bring all these things to this side, you will have the equation like this, right? D square x by dt square plus k by mx equal to 0. Now instead of k by m, you write omega square, where omega is the angular frequency of harmonic oscillator. Then the above equation reduces to d square x by dt square plus omega square x equal to 0. This is a very important equation for the differential equation of simple harmonic oscillator. Now our next aim is to find a solution for this differential equation given in equation 1. For that, let us start with acceleration. We know acceleration is d square x by dt square. Now that can again be rewritten as d by dt of dx by dt. That is right. Same, it is the same as d square x by dt square. Okay. Now you d by dt is kept as such. Now what is dx by dt? It is v, velocity. So this will reduce to dv by dt because this term is v. Okay. Now this dv by dt, we can again rewrite it as dv by dx into dx by dt. When dx and dx cancels, it is actually dv by dt, same. So you are rewriting. Okay, now again this dv by dx is kept as such, dx by dt is v. Okay, so for acceleration d square x by dt square, we have this expression. Now just substitute this expression in your equation 1. What is your equation 1? D square x by dt square plus omega square x equal to 0, right? So in place of this d square x by dt square, you use this one. So you will get like this. Okay, dv by dx, v is equal to minus omega square x. It is very easy to follow, right? Now next, just you rearrange, that is v dv, it is kept here, dx is taken to RHS side. So you will have v dv is equal to minus omega square x dx. Now you integrate LHS and RHS. What is integral v dv? It is v square by 2. Okay. Now is equal to minus omega square is kept as such because it is a constant. What is integral x dx? It is x square by 2. Okay, this one plus constant of integration c. Now our aim is to find the value of c. In mathematics you might have studied. Once you get a constant of integration, you apply boundary condition to find the value of that constant of integration. So here the condition that we are applying is at x equal to plus or minus a, v equal to 0. So your equation 2 will become, that is equation 2 becomes, put x is equal to a, here x equal to a. So it will become minus omega square a square by 2 plus c, but v becomes 0. So it will be 0 is equal to minus omega square a square by 2 plus c. So from here C is omega square a square by 2. Now substitute this value of C in equation 2. So just substitute that value C in equation 2. So equation 2 will become like this. So from here 2 is common, that will get cancelled out, and then in the numerator you have V square equal to omega square is common, that is omega square a square minus omega square x square, right? So V is equal V square equal to omega square is common, then a square minus x square. So what is V? V equal to omega root of a square minus x square. That is equation 3, and that is the velocity of the particle executing simple harmonic motion. Just by heart this equation, because for problems you may have to use this. Okay, so velocity the formula to find velocity is V equal to omega root a square minus x square. Similarly, you have a formula to find acceleration also, that will come next. Now we can rewrite equation 3 as see here velocity we know it is velocity is dx by dt. So dx by dt, this is kept as such. Okay, now from here what is dx? Dx is equal to, take dt here. Okay, dx, so dx is kept as such, this one is taken down, so dx by root a square minus x square is equal to omega dt. You are just rearranging the above equation. Now just integrate both sides. On integrating this one, integral dx by root of a square minus x square, that is, there is a standard form which you might have studied in your 12th standard. When you are having an integral of the form integral dx by root of a square minus x square, its integral is sine inverse x by a. Okay, that is written here. Then in omega dt, integrate. Omega is a constant, integral dt is t, so omega t plus phi, it is a constant of integration. Okay, now from here we can write as here x, this implies x by a equal to sine omega t plus phi, right? So what is x? X equal to a sine omega t plus phi. This is how you got this statement from this one. Okay, phi is the constant of integration. Now this equation 4 is the solution of differential equation. So you have what was the your differential equation for simple harmonic motion? It is d square x by dt square is plus omega square x equal to 0. Now finally you have find out the solution of that differential equation. What is it? X equal to a sine omega t plus phi. X is the displacement, a is the maximum displacement, that is amplitude, omega t frequency part, and phi is the phase change. Okay, now we also got a formula to find v. What is it? V is equal to omega root a square minus a square. Similarly, in order to find acceleration also you have a formula. Just by heart that formula also, because you may have to use this while doing problems. To find a is acceleration is minus omega square x, that is, they will give the value of omega and all, and you will have to find the value of velocity and acceleration. Okay, so here we have studied 4 equations. One is the differential equation for simple harmonic motion. What is it? D square x by dt square plus omega square x equal to 0. Now its solution, x equal to a sine omega t plus phi. Formula to find velocity, v equal to omega root of a square minus x square. Formula to find acceleration, minus omega square x. Now here you see there is a negative sign. What does that indicate? That means acceleration is oppositely directed to displacement. Okay, now note some point that acceleration is maximum at x equal to plus or minus a, that is at the extreme positions. That is, if you have something like this, these are the extreme positions. So acceleration will be maximum at the extreme position and 0 when x equal to 0, and that occurs at the mean position or equilibrium position. So here we have represented displacement in terms of sine function, that is x equal to a sine omega t plus phi, right? You can also express in the form of cosine function. Then the solution will become x equal to a cos omega t plus delta, where delta is nothing but phi minus pi by 2, or phi is equal to delta plus pi by 2. That no need to mention. This paragraph you have to learn, that is you have to mention how acceleration varies as per the value of x. Okay, so in today's class the probable questions are uh, define periodic motion, give examples, what is period, then define oscillatory or vibratory motion, give examples, then define simple harmonic motion or explain simple harmonic motion with examples. Then what is distinguish between linear and angular simple harmonic motion. Then derive the differential equation of simple harmonic motion, and finally find the solution for it. This may be asked as an essay question, so you have to combine these two. First you have to find the differential equation for simple harmonic motion, and then after completing this you have to write the uh, how to find its solution. That so question will be like this, that is derive the differential equation for simple harmonic motion and give the its solution. So you have to combine these two and write, so that will be like an essay. Okay, so study this very well, these questions very well. Okay, thank you.